We want to extend the class of objects we study to include manifolds with boundary. This will be very useful for building a theory of integration on manifolds. Many familiar geometric objects that we often study are actually not manifold. For example, let's look at the closed disk in R2. This is not a manifold because if you take any point P here on the boundary, then no neighborhood of it is homeomorphic to an open subset of the plane. So the closed disk is not a manifold in the usual sense. However, we do have neighborhoods of this point P that are homeomorphic to neighborhoods of the upper half plane. Or I should say the closed upper half plane. Thus we want to extend our study to geometric objects that are locally homeomorphic to open subsets of closed upper half spaces of Euclidean spaces. These will be called manifolds with boundary. So let's define everything formally. So inside any Euclidean space Rn, we define the closed upper half space to be the set of points with the last coordinate greater than or equal to 0. Now, a topological manifold with boundary of dimension n is as usual a second countable Hausdorff topological space that is locally homeomorphic to the upper half space Hn inside Rn. So that means that at every point B we have some chart on M, right, from an open set of P. So what does that mean? That means that for every point P in M, we should have a homeomorphism from some neighborhood, open neighborhood of P, to some open subset of the upper half space Hn. We make an exception for the case when n is equal to 1. This could be an open subset of H1, this right half line, or an open subset of this L1, this left half line. That's fine too. So that's the definition of a topological manifold with boundaries. Again, a topological n-manifold with boundary is a second countable Hausdorff topological space that locally looks like the upper half space Hn inside Rn. Now we want to talk about smooth manifolds with boundary. So just like in the case of general smooth manifolds with boundary are manifolds with boundary with a smooth atlas. That is, with a collection of charts that cover it, such that the transition maps are smooth. So in particular, they must be diffeomorphism. Let's review what the transition maps are. Let's say we have two charts, so u, phi and v, psi. Then each of these charts, phi and psi, give a different coordinate on u intersect with v. So we want to know what is the relationship between these two coordinates. Say if we have a coordinate of the point P under the map phi, so it corresponds to a point here. We want to know what is the corresponding coordinate, right, of P under this map. Well, to find that out, we can just apply phi inverse, right, and then psi. So that composition, right, this map, it's called a transition map. From phi of u intersect with v to psi of u intersect with v. We think of that as a change of coordinate map. For a smooth manifold with boundary, just like for a smooth manifold, we require the transition maps to be smooth. In particular, this means that they are all diffeomorphism, because their inverses are also the transition maps, and those are also smooth. Alright, so that's the definition of a manifold with boundary. Now for manifold with boundary, not all points are made equal. Now we will have interior points and boundary points. So we'll talk about that next.